Okay, recording in progress. Welcome to our class today, Thursday, January 27th, 2022. Guys, as you know that next week that the classes will be in person. So, as I mentioned at the beginning of the course, that the lectures of this class will be online. Tutorials, midterm, and final exam will be in person. Some of you asking if we can have a recording of tutorials. It seems to be quite difficult because we don't have the tools to record the class. We'll do our best. However, the tutorials will be conducted in person. There are 4 tutorials. One before the deadline of assignment 1 and midterm. The second one before the second assignment. The third one will be before the group assignment, and the last one will be before the final exam. So I hope those are clear to you. The lectures will be delivered online on every Wednesdays and Thursdays through the term. Is that clear? When is the first tutorial? The first tutorial will be conducted on last Friday before the reading week. Okay, because the midterm will be the first Friday after the reading week. What do you mean by how often are the tutorials? Brandon. You are welcome, Amanda. Brandon, what do you mean? I said we have 4 tutorials through the term only. So 1 before the midterm and the deadline of assignment 1. The midterm will be Friday, March 4th, I believe. So the tutorial will be the Friday before. The second tutorial will be it will be concentrated on assignment 2 only. So it would be before the deadline of assignment 2. The third one before the deadline of the group assignment, and the fourth one before the final exam. So they are only 4 through the term. Even it's in your timetable, it's every week, but we have only 4 tutorials through the term. So I hope this is clear for all. I believe that we have 2 questions yesterday. So who will be the volunteer? Okay, so Mahira, go ahead. Yes. You can share your screen and answer the first question.
Okay. So for the first question, can you see my screen?
Yes.
Okay, so for the first question, the role of the loop transition is that we don't care what's the first value or the last ones. It could be either 0 and 1, because what we care is that the machine accepts all strings that contain 11010. So if we didn't have them, for example, that means it would have exactly 11010, and that's not what we want. So this is why we have them, so that it accepts the language that the machine wants.
Okay, thank you. Any question to Mahira, guys? Okay. Okay, thank you, Mahira. You can stop sharing your screen. Okay. Longi Lee, you can share your screen and answer the second question.
Sorry, sir, I was in the bathroom.
Sorry?
Sorry, I was in the bathroom.
Okay. So you are not volunteering to answer the second question, right?
Sorry, not right now.
Okay. Ardhaya Bansal, are you volunteering to answer the second question?
Yeah, I can do that.
Okay, go ahead and share your screen, please.
Sure. Can you see my screen?
Yes.
Okay, yeah, so this question was the DFA, basically, that accepts the language of numbers that are divisible by 3. And I think basically your question was just like explain sort of how this works. And I mean, in the context of this question, when you think about numbers that are divisible by 3 or divisible by any really number, like the number of states is basically that number minus ones or that number. Because if you look here, you have like W mod 3, that can be 0, W mod 3 equal to 1, or W mod 3 equal to 2. If you did like W mod 3 equal to 3, that's the same as W, like it's congruent with W mod 3 equal to 0. So there's really only 3 states. So the 2 ways I guess you can think about this is, one, like you can just write out the numbers that are like mod 3 and just go consecutively and try to identify patterns for these like state transitions. So for example, if you look at, okay, if I have W mod 3 equals 0, I have a binary string, right? So there's 2 options here. Either I'm going to append a 0 or I'm going to append a 1. So if I append a 0, what happens? Well, if I append a 0 to 0, it stays 0. And then W mod 3 is still congruent to 0. So if we call that Q0, appending a 0 to the binary string, it stays in that state. But if we append a 1, okay, if I append a 1, like if I append a 1 to 0, the number becomes 1. And so that's congruent to W mod 3 equal to 1. So then the state transition would be from Q0 to Q1. And so you can do that for like all of them, but I find like a more intuitive way to think about it is like just consider what it actually means to append a binary string with 0 or 1. So if you append a binary string with 0, what does that mean? That means to multiply by 2, right? And if you append it with 1, that means to multiply by 2 and then to add 1. So if I have a number that is divisible by 3 and I multiply that by 2, so let's say that's 3, 6, whatever, I multiply by 2, it's going to still stay like divisible by 3, right? Like 3 times 2 is 6, 6 times 2 is 12. Those are all divisible by 3. But let's say I multiply by 2 and added 1, like 3 times 2 plus 1 is 7. And so multiplying by 2, that's divisible by 3, but adding 1 adds 1 to the remainder. So then your state transition is going to be to Q1. You can think about it the same way for, okay, if I'm in the state Q1, my number is 1 dividing by 3 has a remainder of 1. Okay, if I multiply by 2, that remainder doubles, right? So now my remainder is 2. That's why the state transition, when you append a 0 to the binary string, goes to Q2. If I multiply by 2 and add 1, well, that's actually going to go back to Q0 because the remainder is 1 times 2 is 2 plus 1 is 3. And that's congruent to W mod 3 equals 0. So then you go back to Q0. So you can just think about it like that as well, and then just draw it out. This is the state transition diagram. In the class notes, I saw it like this, except this one shouldn't be a 0 because this is a DFA. So it can't be going like 0 like for 2 transitions. This should really be a 1.
Yes, you are
yeah.
correct. This is a typo, guys. Correct it at your class notes. Okay, thank you. Questions? Gareth, where all the tutorials that are posted? It depends on the progressing, when we will release assignment 2, when is the deadline, when is the group assignment will be released, and the final exam when it will be. So these are like, I can't give approximate date, but it is not mandatory. So but the first tutorial, it's already, since we decide the date of the midterm, so this is easy to be announced. So I will, after the class, I will send an announcement for the first tutorial. but for assignment 2, 3, depending on our progress, you know. But I'll make like a plan to give like approximate dates for those. Okay, guys. Do we have any other question for volunteers, or that's it? I think 2 questions only, right? I said I will give approximate dates for assignment 2, 3. For the final exam, it's not my job, it's the registrar office. So they will, as they promise us, they will release it sometimes during February. I believe maybe, I don't think next week, maybe the week after, they will release the final exam schedule. But for assignment 2 and assignment 3, or the group assignment, I will give like approximate dates for those and the tutorial session. We will try to go with it. However, if something changed, we delayed in certain handout, it took more than expected, so we can amend our schedule. But I will put like, you know, a course plan with dates, but these dates are not mandatory. But for the midterm and the first tutorial, no, it's done. I will release the announcement right after the class. And I will try also to post the videos tonight for today and yesterday, if YouTube allowed me to produce the HQ version of the class. Okay, guys. Yesterday, we explained, I think, a class note 3, right? I believe, yes. Class note 3, we are done with it. Yeah. Okay. So today we'll talk about class note 4. Let me share my screen. Can you see my screen? Yes, okay. So this is a class note 4. It is uploaded in OWL under the class notes and resources tab. So example, assume we have a language, we call it L2. This language has a string, we call it X. The cardinality of X equal 3. So the length of X is 3 symbols, where X belong to an alphabet that belong to 0 and 1. So to satisfy the condition that the cardinality of X is equal 3, then I start at the Q node. If I receive either 0 or 1, I'll move to Q1. Then if I receive another symbol, whatever it is, I'll move to Q2, then to Q3, and this is the final state. Okay, then if we receive more, this is the accept state. But if we receive a string that more than 3 symbols, so it's not belong to that language. That's why we added the Q4 with 0 and or 1, then whatever repeated, and this is the dump state, we call it, or dead state. Is that clear? Okay, we talk about regular languages. So at the beginning, I need to explain some regular operations, because we will see those also in handout 4. Because at the end of handout 4, we might touch the hardest topic for the student in this course, which is the pumping lemma. You will understand it, don't worry. However, it's a bit rigid topic. So let A be included or equal to clean star or sigma star. First, we have the union operation. What do we mean by a union? That we are unifying the two sets in one set. A union B equal X, where X belongs to A, or any symbol or any string that belongs to B also. Concatenation, we are merging two strings together. The order here is important. You remember first class? The order here is important. So if string A is AB and the string C is CD, I cannot say the answer is CDAB. It should be ABCD. The order is important in concatenation. So if I have here A equal AB and B equal 1, 2, 3, then what is AB? It is A1, B1, A2, B2, A3, B3, and so on. Star operation. What do we mean by A star? It is equal symbols x1, x2 to xk, where k is greater or equal to 0, and each xi belongs to A for all i's. Example, if we have a language that consists of two symbols, which is 1, 0, and 0, 0, 1. So what is A star? It is epsilon, don't forget this, which is the empty string. 1, 0, 0, 0, 1, 1, 0, 1, 0, double of this. Then 1, 0, 0, 0, 1, the combination of those. Then 0, 0, 1, 1, 0, and so on. Back to non-determinism. We talk about this last class. From a state Q on an input symbol A, the automaton can go to the multiple state. This is as simple as it is, that we can go to multiple state. It can go to 0 or more states. We denote it by the symbol K, where K is greater or equal to 0. Computation happens simultaneously in parallel at the same time along each of these paths. As you remember yesterday, we have multiple paths, so the computation will go at the same time for all these paths. Additionally, the non-determinism, it has the epsilon transition. If there is epsilon transition, we will move without an input. We will move from state to another without an input. Then the automaton moves to the state Qi and the Qj without reading the next input bit. Guys, as you know, that the basic thing in the computer memory is a binary cell. What do we mean by binary cell? We call it bit. The bit can include 0 or 1. So each symbol in a string, it will be, or it will represent a bit. Each 8 bits equal 1 byte. Each 1024 bytes equal kilobyte, and so on. For kilobyte, megabyte, gigabyte, terabyte, and so on. An input is accepted when, if there is some computation path that lead to an accepted state, to a final state, this state with double circle, which satisfy the condition. Non-determinism finite automata. For example, I have a Q node. If I receive a 1, I might stay at Q0 or I can go to Q1. This is the meaning. At Q1, if I receive a 1, where I go? I'll stay at Q1. In Q1, if I receive a 0, I'll move to Q2 or epsilon. But if I receive a 1, I will stay at Q1. Q1 with epsilon, Q1 with epsilon, Q1 with epsilon, I'll go to Q2. Note the transition are labeled with symbols from the set epsilon sigma equal epsilon sigma union the epsilon set or the empty set, or consider an input equal 0 1 0 1 1 0. So I receive 0 1 0 1 1 0 0 at the Q note. Where I'll go? I'll stay at the Q0. Initial state. I'll stay at Q note here. When I receive a 1, either I stay at Q2, a Q0, or go to Q1. See here. When I receive a 1, I stay at the Q0. This is what we said. Here we receive a 1. I can stay at the Q note or at Q1, or when I am at Q1 or to Q2. Q0 to Q2. Then with 1, I can go to Q0, Q1, Q2, Q3. Here I'm showing you how is the path will go. Then with the last 0, I go to Q0, Q2, or Q3. And we will see here that Q3 is an accepted state. So by definition, we have an accepted state present in our example. So input is accepted. You need to read it well, put the paper in front of you, and you can go step by step to understand. If we are in class or in person, we'll go on step by step to draw this transition table. So, and try at yourself different string, like 1 1 0 1 1 0 0 0 1 0 0, and see if it will lead to an accepted state or not. If not, if you stop at a state that it's not final state, then what will happen? You will reject the string or not accept. Questions? Okay. So let's see. Can you see class note 5? Ryan, why aren't we go to Q1 in the second bit? Okay, let me see. This is 4. Zero, 1. Because here you have to understand what we are saying. If in the first occurrence, when I receive the 0, I stay at Q note. In the second one, if I receive a 1, I might stay at Q0 or I can move to Q1. And since there is an epsilon transition, also I will include the Q2. Is that clear, Ryan? If you see here, we put the Q note, Q1 and the Q2. Why we put this Q2? Because there is also possible epsilon transition. from Q1 to Q2, which means that if I receive a 1 and I took this path, I'll move to Q1, and with epsilon, I'll move to Q2. That's why we include it here. Okay, you are welcome. Any other question, guys? Don't be shy. Ask. Okay. Okay, let's go to 5. Again, we talk about those last class, but this is a kind of a class note as a revision. What are the differences between deterministic finite automata and non-deterministic finite automata? So the deterministic finite automata, when I'm in state Q and receive a symbol A, I'll go to the next single state. I don't have other option. In an FA, if I receive a Q and a symbol, same as in our previous example, the 1, I can go to multiple state. I can stay at Q0, or I'll move to Q1, and with epsilon transition, I'll move to Q2. So I can move to 3 states, which means 3 different paths. Okay. Single computation, multiple computation happening at the same time, in parallel, simultaneously. No epsilon transition. Here we have an epsilon transition. What is epsilon transition? It's a transition that will move me from one state to another without any input. Except if the computation ends at an accept state, except if one of the computation paths end at accept state. Clear, guys, the differences? Might be one of the midterm question, guys. Midterm is not an open book, huh? Sometimes I give some hints. You can start it. I didn't write the exam yet, but it's a good question. Okay, now. NFA, non-deterministic finite automata formal definition. The definition before here, or in 4, in class note 4, is not a bit formal, but it clarifies what do we mean by non-determinism. Here is the formal. It's a 5 tuple. N, we call it N, which represent non-deterministic. Q, which is set of states. A finite set of state, to be more accurate. Sigma, which is the input alphabet. Delta, which is the transition function. Q naught, which is the starting state. F, which is the accept state or states. I might have more accept state, more than one accept state. And the alphabet, it's also include the alpha epsilon. What do we mean by the alpha epsilon? Which is the alpha that we know in addition to the epsilon symbol as an empty string. And normally, be careful, we use the set symbol because we are talking about alphabet. What is the cardinality of this set? 1. What is the cardinality of epsilon itself? It's a 0. Clear? For a set A, 2 to the power A denotes the power set of A. Any set, how we know the power set of it? It's 2 to the power set of A. We say that N accept an input W, whatever it's A1, A2 to AN. If we can write W as W equal B1, B2 to Bn, where Bi belong to sigma, epsilon, and there exists a sequence of states R0, R1, R2 to Rm, not necessarily distinct, such that R0 equal Q naught, initial condition, Ri belongs to delta, where Ri minus 1 with Bi transition condition for each I from 1 to M. Rm belongs to F, which is acceptance condition. Language of NFA, non-deterministic finite automata, we call it L of N, which has a string W belong to sigma star N accept W. This is a condition. Example, L1 has a string W that belongs to 0 or 1 star. Third last symbol of W is a 1. Third last, even it's 10 character. From the right, the third last is 1. It should be a 1. So I'll start initial state 0, 1. Then the third last symbol from Q0 to Q1 is 1. If it's a 0, I will stay here. Then whatever here is 0 or 1, or here 0 or 1, I can stop, because we need the third last element from the right. So if we have 1, 1, 1, 0, let's see. 1, we'll stay at Q0. Then we receive the last one, 1. I move to Q1. Then I receive another 1. I'll move to Q2. Then I receive a 0. I'll end at Q3. Then accept the string, because the third last element is 1. Clear, guys? Let's have another example. So this is in a class practice. So next week, I need a volunteer to show us for 1010 the answer, and show that for each DFA for L of K, W belong to the kth last bit is 1. Can you draw a DFA for this? This is the second question. So we need a guy to solve this one, 1010, using this method, and the other question, this one. This is in a class practice, so I need 2 volunteers next class. Example 2. I have a language L2, has a string W belong to a language that consists of 1 symbol, any. The length of W is divisible by 2 or by 5. You see the question become more complicated. We will use epsilon transition to differentiate between the 2 conditions, divided by 2 or by 5. So we go into 2 parallel paths, one for divided by 2 and the second one divided by 5. How we will do it? With epsilon transition, and this is the benefit of epsilon transition with non-deterministic finite automata. So we start at the Q0. We will either move to the 2 or 5, and we said both will be running at the same time. So if I have 2 zeros divided by 2, then I'll end at in the state and I'm done. If it's by 5, 1, 2, 3, 4, 5, and I will end at Q3. But you see, if I will do a non-deterministic or deterministic finite automata for this question, it will be quite difficult. It could be, but it will be more complex, because I need to jump over those epsilon transition, and for each path, I have to design it in a way that it could determine it's divided by 2 or by 5. And we talk about this equivalence of NFA and DFA last class in handout 3. Every DFA is also an NFA, which is theorem 1. let n equal b and NFA, there exists a DFA, and here we call it a prime, such that L of n equal L of d. Deterministic and non-deterministic, they will be equivalent. So construct of D, non-deterministic, Q1 equal 2 to the power Q, and this is the power set. Let A belongs to Q, then delta prime A capital A, and it's a union of all states that belong to A, where R, when I receive a symbol R, I'll move to or a state A when I receive a symbol A, or A belong to the alphabet. So don't bother yourself with these like proofs and mathematical thing. It's just for your knowledge. And what the end of this final state means, have some final state that would accept that language. What about epsilon transition? Let R belong to Q. Here how we add the epsilon transition mathematically. We define delta prime to accumulate epsilon transition. So this will include the epsilon. We will not prove that. If you are interested, read it from any book of the both textbook. The proof is there. I'll not ask you about these mathematical proofs or derivatives. Now, example. Assume that we have the language L that consists of a string W, where the second last symbol in W is 1. So it's easy. So whatever the second last one, and here whatever 0 or 1, the last symbol, will end at accept state. Construct a DFA that have 2 to the power 3 equal 8. Will do 1 when I need. So this will do move this one. Here we ignore states that are not reachable from the start state, are known as dead states. So we don't draw them the dead state. That's why we don't show them in the above example. In this example, to make the 2 to the power 3 equal 8. Theorem, here in the language or regular languages, if we have L1 and L2 are regular, then L1 union L2, L1 concatenate L2, and L1 star are also regular. For regular language, we assume that there is an undeterministic finite automata accepting it with a unique accept state. This for regular language. Remember this. With a unique accept state. Proof. So if I have a language L1 and L2, then I have NFA for N1 and N2. Start state Q1 and Q2, accept state are R1 and R2. So at Q with epsilon transition, I go to N1 and N2, then I will end at R. So this is for the union, to prove the union condition. And here to prove the concatenation. This is N1 with epsilon transition. I'll move to N2 and I will end with R, which is accepted state. So L1 intersect L2 is a regular concatenation. And this one for L star with epsilon, I'll move and back with epsilon, then I will end with R. So this is a proof, bigraphical proof. We prove that L1 star also is regular. Questions? We'll stop here today. See you next class with handout 4, which is a closure property of regular languages, regular expression pumping lemma. So we'll talk same as what we talked today here. Then we will end with regular expression. Then we'll move to the pumping lemma. So thank you, guys. Thank you all. Varon, Mahira, Zachary, Ryan, Austin. Tayi, Faris, Timothy, Alex, Abdullah, Colin. Okay, Connor, just to clarify, the lecture will stay online at the same time Wednesday and Thursday. Yes, Connor, will stay online. Lunji, thank you. Connor, thank you. Lunji, do you have a question or shall I stop recording and end the class? Okay, see you.